Okay, so this is what we can do. Okay, but immediately we have a serious problem. Okay, this problem has existed for a long time in Stackelberg games. That is time inconsistency. Okay? And in this work, we will adopt a notion called t-selves, okay, and then develop time consistency. Okay. Actually, this notion was introduced quite recently by mathematicians for continuous time decision models. But for the discrete time counterpart, there is already a long history. Okay, now let's have a look at the model. Okay. You can see here we have two types of players. Okay, A0 is quite different from other guys. Okay, it's called the major player, okay, or the leader in the context of Stackelberg games. Okay, why it is a major player? We can check the structure. Okay, you can see here the state, the control and the state of the major player directly enter the dynamics of AI called a minor player or follow. Okay, so you can see each minor player receives strong influence from this major player. Okay, this big guy. Okay, and in contrast, when we consider the minor players, they mutually have a very small influence on each other, okay, and also on the major player, okay, because of the scanning appearing in this empirical distribution. And in the model, here we take U as the control. Okay, we also have some assumption regarding the initial conditions. Okay, so this is the basic model with a major player, the leader, okay, and the n minor players follows. Okay, and next we can introduce the cost function of the players. Okay, here for simplicity, we do not take a terminal cost. Okay, and again, if you have a look at the structure of the running cost, okay, you can see the big influence of the major player on the minor players. And for the LQ case, the drift and the running cost will take this kind of particular form. Okay. In this work, we will mostly work out the LQ case, okay, but this general procedure is applicable for nonlinear models, although more difficult, and also for some other modeling like discrete time, discrete state. So for the dynamics, okay, here we introduce this compact notation. Okay, so it means given this measure here, okay, this is used to describe the mean field generated by the minor players follows. Okay, so this is the mean field. So basically here for this bracket term, okay, it means the first moment of the mean field. Okay, here we use this notation. When you have G here and then the subscript, okay, it means you average this G. Okay, now if you just have the state Y, you average. Okay, it means the first moment of the mean field. Okay. And for the quadratic cost, okay, you can see some kind of tracking. Okay, so for example, here we have the major player. Okay, we have the first penalty term. Okay, we have the difference between its own state and the other term as a linear function of the first moment of the mean field. Okay, and also we have the penalty on the control energy. Okay, then for the minor player, we need the linear compilation of the major player state and the mean field for tracking. Okay, so basically each minor player should respond to the major player and also the whole population of minor players. Okay, and here for the control penalty, we have this special structure. Okay, so here we have the minor players its own control. Okay, the major players control, and also importantly the cross term for the controls. A few remarks about the structure of our cost. Okay. So here we need this cross term. Okay. If the weight matrix R2 is equal to 0, then leadership will disappear. Okay. And this is a well-known fact in the conventional theory of Stackelberg games. Okay, when you just have one leader, one follow, okay, you need this kind of cross term. Okay, we have some background about this kind of cost structure. Okay, for example, it can arise in applications in macroeconomics, okay, actually in monetary policies. Okay. You can see the paper in American Review of Economics. Here some related work about this class of models. Okay. In the economic literature during the early days, we can see some static models, okay, with a major player and an ocean of minor players. Okay, but it's usually for cooperative games. Okay, so that means the focus is to study the Shapley value of the game. Okay. So in this work, it introduces the modeling of mean field games with a major player. Okay. The motivation for this kind of problems is obvious. Okay. You can think of, say, a central bank, which is very big, okay, powerful, and a large number of smaller banks, okay, or businesses, okay, which are much smaller. And also in a stock market, you can think of one or a few institutional traders, very powerful. Okay. Then a huge number of individual traders, much smaller. Okay. Actually, indeed, in the recent work by Jamango and his co-authors, they used this kind of major player model for liquidation problems. Okay. And here we also mention the nonlinear generalization by Laurent Keynes, okay, and the Kamala and the Zhu, and the Kamala and the Wang, and the recently we can see some modeling and analysis in the papers of Lazrak and the PI here and his co-authors. Okay, they developed a powerful approach using master equations. Okay. In particular, in the paper of Pierre and his co-authors, they examined the convergence problem for the major minor player model. It's certainly a very difficult problem, but the paper is very well written. We actually got a lot of inspiration from their work for this project. Okay, some further background about this kind of major minor player model. Okay, they consider leadership. Okay, actually, in an early paper by Wang and Zhang, they consider a discrete time model. They use dynamic programming. For their approach to work, they actually depend on a very special structure of the model. Okay, it must be very simple. Okay, otherwise, it's hard to play dynamic programming. And also, very recently, we can see the interesting applications by Aurea Kamala and their other courses. And also, we can see some other important works by Professor Mansusan and the Moon and Professor Basha and the Ali. And the next one by Hu and Host is essential for mean-field type model with a leader and I follow. Okay. For the analysis here, okay, in the second category, usually they do not have time consistency. Okay. In particular, when you look for a solution through the maximum principle on a fixed time interval like this one, okay, you will not get time consistency. Okay. This is actually different from many existing contributions on mean-field games. Okay. When we use dynamic programming to get the solution, okay, essentially you will have time consistency. Okay, but for this class of models, somehow the situation is a little bit messy. Okay. We do not have time consistency so far. Okay, and also I should mention the work by Professor Xinguo and his student here. For the discrete time case, okay, it's also an interesting problem, okay, highly non-trivial. For this work, what we want is basically to achieve time consistency. Okay, we will borrow some ideas in the recent progress on this subject, okay, that is on time consistency for optimal control problems. Okay, so for our further development, we will start by considering a two-player mean-field limit model. Okay, so here in this picture, we can see one major player, okay, and then a single representative minor player as the follow. So essentially here we are just take the two SDEs introduced earlier, okay, but we immediately go to the mean-field limit. Okay, so that in the early model, okay, when we have the actual average term here, okay, for the mean field. Now we just go to the mean field limit. So now in this picture, only two players are visible. Okay, here we have the third equation. It is for the dynamics of the mean field generated by a continuum of minor players. Okay, you can regard this as a Fokker-Planck equation in a weak form. Okay, here we use G as the test function. Okay, so that in the end we can write this kind of ODE in a weak form. Okay. Here we have a little bit discussion about the mean field. Okay, actually, for our formulation, we do not directly take this mu s as the law, the conditional law of the minor player here. Okay, here is the reason, because we can assign arbitrary initial conditions to this minor player. Okay, and for this mu s, it can be arbitrary. Okay, so they can be kind of independent. Okay, for this reason, we do not take this mu s as the conditional law. Okay, now we further do the mean field approximation in the costs. Okay, so in the end, we have the major players state, the minor players state, and also this mu s as an extended state. Okay, so essentially, this mu s as the mean field provides the medium for the interactions of the players. Okay, and here we can further introduce the value function. Suppose somehow here we already have the Stackelberg equilibrium. Okay, then we can define the value function in this form. Okay, we have the initial state. Okay, given by x0, xi, and mu here. Okay, mu is a part of the state, and the given the equilibrium strategies, okay, we can specify the value function. Okay, so here somehow the description is different from stochastic optimal control problems. Okay, because we know in a stochastic optimal control, you can specify the admissible control site. Okay, then you define the value function as the infimum of the cost given the initial time and state. Okay, but here we cannot really do that. Okay, we can only have a partial specification. That is, somehow, if we have the equilibrium strategies, okay, then we can define the value function. Okay, in order to completely finish the specification, we need to go down. Let's check what's the idea to eventually determine the value function. Okay, we will use dynamic programming. Here, the approach is a little bit special. Okay, for dynamic programming, we actually borrow the idea of t-selves. Okay, in the literature, okay, we will discuss that later on. Then the game is like this. We consider a very short period. Okay, so in this case, actually, the two agents live in this world. Okay, they play a game for this short period. Okay, after that, they die. Okay, they leave this game, okay, which is taken over by other agents. Okay, so this is how we can do dynamic programming on this short period. In the end, we can somehow specify the following HJB equations, essentially master equations. Okay. We got a lot of inspiration from the classic paper by Pierre François here in audience, okay, and the Professor Leon and Professor Lazrak. Okay, so in order to complete the specification of the HJB equation, let's introduce some quite standard operators. Okay, essentially, they are for the generators of SDEs. Okay. In the specification, in the end, we needed to introduce the derivative with respect to measure. Okay. In the end, a new variable y will pop out. Okay. So initially for our value function, say for v0 here, okay, we have 3 arguments. Okay. After the differentiation, we get the new variable. Okay. This is very well known. Okay. We can see the loads by PI. Okay. Okay. So for the HJB equation system here, now we have 0 terminal conditions due to our structure for the costs. Okay. We have 0 terminal costs in G0 and Gi. Okay. Here it should be V sub I. We follow this classic paper for differentiation with respect to for the related master equations with a major player. Okay, you can see 2 closely related papers. Okay, actually, I would also mention that for the work of PI, if we specialize to the LQ case, we can compare with the early paper in 2010. Okay, we can show that there is an equivalence, okay, for the LQ case. But this paper is more general. They can deal with nonlinearity. Okay, general, not necessarily linear, not necessarily quadratic cost. Okay, so we want to get the leadership for the major player. Okay, so let's check how we can implement the idea of the leadership. Okay, actually, we will carry out 3 steps regarding the optimizer in the 2 HJB or master equations. Given the action of the major player, okay, here we consider a short period. Okay, so for this short period, the leader takes the control U0. Okay, given U0, we can find the best response of this minor player. Okay, essentially, we find the best response of the whole population of minor players. Okay. Here we deal with the representative minor player. So we try to minimize this function H1. Okay, this is essentially the negative Hamiltonian. Okay, if we
Yes, excuse me, just a quick question. You said that you restrict the game to this small duration epsilon, but do you give like a terminal cost at the end of this small period?
Yes, in the end we will use the terminal condition to
not at capital T, at T plus epsilon. You see?
Yes, actually it does not matter. Yeah, you can. Actually, if you are willing to spend more time, actually you can move this small interval to the end. You start to do it recursively in some sense. But here, actually we take this little t as a moving reference time. Okay, it's adjustable. Okay, if you wish, you can start with the very end part. Okay, so now in the minimization, we can see somehow this U height has already appeared in the second line. Okay, this is not a typo. The point is that here, when we look for the best response, okay, it's actually for all the minor players. Okay, so essentially, it's like a Stackelberg large game. Okay, the large game is played by all minor players. For this reason, when we look for the individuals, okay, this single guy's response, we have already taken into account what all the other minor players are doing. Okay, so then in the end we can get U height here. Okay, the good thing here is that in the calculation, actually we only need to use the first two lines to get the minimizer. So that means actually when we have determined this U height I here, actually this one is precisely the one we have already used. And the next, in the second step, we check the adjustment by the minor player. Okay, so it's played like this. Initially, the major player announces this action, okay, and they anticipate what the minor players will do. Okay, then this major player further adjusts its action U0 start. Okay, so this is how we can figure out U0 start. In the calculation, actually, in the second term, okay, for the mean field part, actually U height I has already contained the effect of U0 as shown here. Okay, so in the end, we can determine the optimizer of the major player. Okay, and finally, for step 2, we update U height I. Okay, because in this part we have U0. Okay, now we just plug in U0 start obtained in step 2. So we finish the job. Okay, now we have the optimizer for the major player and also the optimizer for the minor player. Okay, so this is how we can select the optimizers in this Stackelberg game. Okay, you can see in this case, actually, we need to somehow iterate the minimization part. Okay, it's different from the large case for the master equation. Okay, for the large case, actually, all of them will select the optimizer simultaneously. Okay, so by the 3 steps here, we can see a clear leadership by the major player. Okay, so by the previous 3 steps in the end, we can derive the following 2 HJB equations. Okay, they are essentially dynamic programming equations. Okay, that's why we can call it just an abstract dynamic programming equation. Okay, we can also follow the usage in the paper of the group of 4. Okay, we can call it two master equations. Okay, so here you can see it's the right-hand side is quite big. Okay, but the interpretation is still quite obvious. Okay, so basically, if the mean field disappears, then it reduces to a standard HJB equation in optimal control. Okay, then for the minor player, we have this HJB equation. Okay, it looks quite complicated. Okay, but again, we have a very simple interpretation for the right-hand side. Okay. And actually for the two equations, in our later calculation, we can show the last two terms with the second derivatives for this term and also this term. They will disappear. They are equal to 0. Okay, so now let's check for this particular IRQ case, what kind of a solution we want to look for. Actually, we can restrict to this kind of solutions. Okay, we call them a quadratic solution to the master or HJB equations. Okay, if we can find two matrix functions P0, P here as the weight coefficient in the quadratic term, okay, and the R0 and R here, okay, then we say we have a quadratic solution for this problem. In the vector here, you can see we have a very simple interpretation for y sub mu here. Okay, so this is basically the first moment of the mean field. Okay, there is a good reason for us to consider this kind of solution structure, because for the linear quadratic case, in the end, we guess only the first moment of the mean field will play a role, okay, in the control law. That's why we restrict to this class of solutions. Okay. We have the first theorem about the solution of the master equations or HJB equations. Okay, so here we have a necessary and sufficient condition to have a quadratic solution. Okay, then a necessary and sufficient condition is to have a solution for this Riccati-like ODE system. Okay, for the two matrix equations. Okay. Actually, here the coefficient matrix A0 and A depend on the unknown. Okay, so we can show this dependence on the next page. Okay, so basically, when we specify this A0 matrix, okay, we need to use the unknown, okay, as the matrix P. Okay, this is used in the value function of the follow. Okay, so we actually need to take this kind of submatrices into A0. Okay, so in the end, A0 itself involves the unknown. Okay, so this is different from standard Riccati equations in optimal control. And for the follow, the structure is a little bit more complicated. Okay, essentially, it is still a quadratic structure. Okay, because here you have this P, okay, and then you have this P0. You have a product. Okay, so you have a quadratic structure. That's why we can still call this a Riccati-like ODE system. Here, this E is just a constant matrix. Okay. And for this Riccati ODE system, we can see, okay, if we have a solution at all, then it must be unique. This is due to the local Lipschitz property of the vector fields on the right-hand side. So by the theorem here, you can see for the solution of this problem, it reduces to testing the existence of a solution to this ODE system. If the previous Riccati equations have a solution on their t, in the end, we can figure out the equilibrium strategies. Okay, so it's kind of a linear feedback. Okay, in the calculation of the second term, actually, we will use the mean field generated by the closed loop. Okay, so in the end, this mean field is a function of t. Okay, depends on delta t. Okay, and for the follow, its control uses this its own state, the state of the major player, and also the mean field. So now we have the following big question: how to interpret the equilibrium property? Yeah, actually, I need to add a remark about the literature. Okay. For the conventional Stackelberg game, actually, this dynamic programming approach is already known. Okay, people know how to use dynamic programming to generate two equations. But the specification of the resulting equilibrium is somehow missing. Okay, there is a good reason because the right way to do that using t-self is a quite recent thing. Okay, okay, now suppose the policies have been determined by solving the two Riccati equations. Okay. Now we check the following, like the continuum of follows implement this strategy. Okay. And now next, let the leader further optimize on their t. Okay, so do another revision of its strategy. So it's like an optimization problem like this. Okay, so all the minor players or follows have already honestly implemented the recommended strategy. Okay, now like the leader further optimize, we ask, what will be this strategy? Is it equal to the recommended one? The answer is no. Okay, so this is quite bad in some sense. Okay, so you can think of an agreement by the whole group. Okay, so all the minor players have already honestly implemented the recommended strategies. Okay, but eventually the follow can do something different for its own benefit. Okay, so there is some sort of a stability problem. Okay, this can be quite serious. So what can we do? Okay, so here is a numerical illustration of this instability. Okay, initially we solve this problem to determine the strategy of the leader. Okay, suppose all minor players or followers have used UI star. Okay, now they need to recompute its strategy. Okay, in the end, it will come up with a new control law. Okay, so here we can see this difference or the revision of its strategy. Okay, so in this case, you can see nobody will really have confidence in this recommended plan. Okay, so it's actually a time inconsistency problem. So here in the following, we will check what's the right way to quantify the equilibrium. Okay, obviously, for the obtained strategies, if we use a performance measure like this, okay, it is not appropriate. Okay, it's not the right one. Well, we need to do something different. Okay, okay, so for our equilibrium analysis, actually we will use the idea of t-selves. Okay, we can see some related literature. Okay, so in the papers of Ekeland, okay, they deal with optimal control problems with non-exponential discount. Okay, and the work of Yang is for mean field type optimal control problems, which do not have time consistency. Also, there is a very nice paper by Bjork and his co-author. It includes both discrete time and the continuous time. And the history of time inconsistency is actually much longer. Okay, this is only for very recent literature. So here is a little bit story about the early literature. Okay, how people discovered this problem. Okay, actually, in the very early paper of Strauss, he considered an optimal control problem or planning problem with a cost like this. Okay, to be accurate, okay, he actually considered a cost structure like this at time t greater than 0, because he cared about a good memory of the past. Okay, so now say this is a 2 day. When you optimize for the next 5 days, okay, you still take into account the past 2 days. Okay, and for his problem, there is a total budget constraint condition. Okay, that's why when you include the past, okay, then the past still can affect the control in the future. Okay. So for a cost like this, when the discount function is non-exponential, you will get time inconsistency. Okay, so the idea is actually very simple. You can thinking of this. So too much. You can thinking of a planning problem. Okay, say this is Monday. Okay, then Tuesday, Wednesday, then Friday. You come up with a plan. Okay, this is the decision plan. Okay, this is what you need to do. Then on Tuesday, you replan again, and you get a different plan, okay, which is different from the restriction of the old plan. So that means what you have figured out on Monday is useless on Tuesday. Okay. So this is the basic idea of time inconsistency. And they are in the many recent works addressing time inconsistency, they actually deal with the so-called mean field type optimal control. Okay. You can see the recent work of Yang in transaction IMS, okay, for a very general mean field type, LQ mean field type control problem, and many references cited in this paper. And this class of problems includes this important problem, okay, this $1 million problem initiated by Markowitz. It's a mean variance portfolio optimization problem. Okay, so that's the related background for time inconsistency in decision problems. Okay, now for our HGB equations, in the end, in order to get a meaningful interpretation or meaningful equilibrium quantification, we actually needed to use this kind of idea, okay, this kind of t-selves. Okay, so suppose we have solved the two master equations, okay, then we can construct the decentralized strategies for the n+1 players. Okay, so we have the leader and the n follows. In the end, we can write down the closed loop dynamics. Okay, in this case, from the point of view of the major player, it sees its own state. Okay, and the in the actual dynamics, okay, it sees its own state, then the state average. Okay, and then this artificial state, okay, this is used to approximate this average. Okay, so for the major player, in the end, it uses the first component, the second, and the third. Okay, for a follow, it uses the 4 components in the system. Okay. But for the control law itself, you can see, okay, for the major player, it uses its own state. Then this mean field state. Okay, but for this mean field state, it is driven by the major player's state, which in turn is driven by this x height n. Okay, so they are all coupled together. Okay, so now the question is how we can analyze the performance of the set of decentralized strategies. Here we have the auxiliary value functions. That is, when we have the decentralized strategies, okay, we can calculate the value functions for the two players, okay, in their closed loop. We have the following lemma about the structure of the two value functions. Okay. And now we are ready to quantify the performance. Okay. So the idea is like this. For the major player, okay, we consider its perturbation, its control perturbation on this small interval. Okay, that is this short period. Okay, and for the remaining period, it's still the same. Okay, there is a good reason to do this kind of perturbation because we take this interpretation of t-selves. Okay? After t plus everything is played by other guys. Okay? It's actually like t incarnations of the major player. Okay? So it cannot really adjust the future plan. Okay? It only adjusts for this short period. So given this deviation to U0, we can think of the best responses of the n minor players on this interval. Okay, again, for the future period, it's played by other guys. Okay, they should remain the same. Okay, so this is the perturbation of the strategy. Okay, and the resulting calculation of the cost. Okay, so roughly you can see, okay, if you move J to the right-hand side, it means J is greater than the original thing, subject to a small perturbation. Okay, so it means J is still quite big. Okay, that's the interpretation. You cannot really go down too much. And in the calculation, we can see, okay, we must introduce a scaling. Okay, so that means for this difference, we need to scale up in order to see useful information. Otherwise, when you do perturbation on such a short period, the difference is almost equal to 0. Okay, it's trivially true. It's trivially true. Okay, if data n is small. Okay, it's a small sequence. So if you scale up in the end, you can get non-trivial information. Okay. So for the minor player, it's actually easier. So basically, it has perturbation just for itself. Okay, it's like a large game. Okay, we consider the perturbation of this single guy. Okay. So it's easier. So again, it means GIN under the new control is above the old cost. Okay. So it means you cannot really go down too much. Okay, so finally we have the main result for the equilibrium analysis. Okay, what we can obtain is the delta n Stackelberg equilibrium for the n+1 player game. Okay, so here we have this this expression for delta n. Okay, so roughly it means when n is very big, okay, and the initial approximation is good, then delta n will be very small. Okay, so in the end, it means here you almost have 0. Okay, so it means in the end, you cannot have essential improvement for this leader. Okay, so this shows the delta n Stackelberg equilibrium property. So for further extension, it will be of interest to include nonlinearity, okay, at least in the cost. Okay, in order for this to be doable, we still need would still need some restriction on the structure. Okay, otherwise the calculation of the optimizers will be very complicated. So to finish, in this talk, we consider mean-field Stackelberg games, okay, and adopt a dynamic programming approach. Okay, the equilibrium analysis is based on the notion of t-selves, okay, and we can establish time consistency. Okay, so thank you for your attention.
Are there any further comments or questions, Minyi?
Thank you for your talk, very nice talk. I have a question about when you have these two the major player can deviate and do better, but can the minor player also deviate and do better?
It's not so better. When, for example, for the minor player, when it improves, okay, if you move this to the right-hand side, you can see, say here that n is very small, almost 0. So it means your new cost is roughly still greater than the old one, subject to a small error. So you cannot really improve too much for yourself. This is for the minor player. For the major player, it's the same. It cannot really improve.
But in the limit game, I mean, like you remember many slides before?
Yes.
You had when you solve the major minor midfield game, and then there is this U not new. Exactly, yeah.
Yes.
Do you have something, is there something like this also for the minor agent?
Here I only discuss the deviation of the major player. Actually, to answer your question, actually we need to further refine the scenarios. For the if the major players, if the leader's strategy is fixed, and if the minor players still play a large game as specified by the original solution here, they will not deviate. But if they cooperate, then it's a different story. They can move away.
Thank you. So the Nash situation will stop them from this. Thank you.
Are there any further questions?
Yeah, so you showed this system of Riccati equation. Do you have a condition under which it has solutions? This is what you wrote when you said about, you talked about analysis of the Nash system. So the system of Riccati equation, does it have solution?
Not always. Actually, you can see if and only if we have a solution.
Yeah,
this is a Riccati equation system.
But do you have smallness condition and showing
yes,
that?
Yeah, okay. If it's a short period, you must have a solution because the vector field is locally Lipschitz.
Could you go back to your simulation and interpret your results on your simulation? Yes. Can you comment on that in the light of your
so this is actually to test the stability of the recommendation. Okay, say initially we come up with the recommendation. So for U0 star and UI star here, in the end we just solve the two Riccati-like ODEs. Okay, so here the top picture is for P0. For the scalar case, we know P0 is just a 2x2 matrix function. Okay, so we have the 4 trajectories. Now, when we do the revision of the strategy of the major player, okay, as indicated here, we need to solve a new optimal control problem. Okay. Fortunately, for the new optimal control problem, we still have a neat Riccati equation. Now it is a standard Riccati equation for optimal control. Here we do not display that, but we can still solve this new Riccati equation, and we can compare with this old one. Okay, with the old one. Then we can show the new Riccati solution is different from the old one. Here we just indicate the difference for one entry in the matrices. Okay, so this is how we can detect this difference.
Great, thanks.
Okay, thanks, Minyi. So I'm still trying to understand the concept. Do you solve in one shot the complete schedule, which will be consistent? It's one shot.
Essentially, you can view this as a one-shot game, because in in the final assessment of the strategies, you can see when we do the perturbation, we take an alternative strategy in this form. Okay, so for the deviation, it's restricted to this short period. So somehow it looks like a static game for one shot.
Yes, but can you pre-compute the complete policy before the realization of
yes.
the stochastic processes?
Yes, actually in this...
it's not going to depend on where you land in the state space?
Actually, for this game, actually not for the remaining period. If you recompute, you just use the old solution, restricted on the remaining period.
You use the old solution. I thought it was inconsistent, and you could not use the old solution.
Can use.
You can?
Yeah. The key thing is that in the quantification of the equilibrium, we should use this specific perturbation.
Another comment is that we see more and more results which depend on existence of solutions to systems of Riccati equation for all these quadratic. So it looks like we really need mathematicians to push the results on Riccati a bit further now. We've known Riccati for a long time, but we're getting new animals here. And it would be,
yes. So, so far, the classical existence results are mostly for optimal control problems themselves.
Exactly.
For this kind of Riccati system, it's less explored.
Okay, I think in the let's thank Minyi Huang once again.